All right, page 311. We were looking at distances yesterday and how there's technically two types of distances that we can calculate based off of the motion of an object or a particle. Those two types were either net distance or total distance. Before we kick off with some more examples today, can we just kind of review or discuss what the difference is between those types of distances, net versus total? Do a refresher.
Net is point B minus point A.
Okay, beginning point minus ending point or vice versa, doesn't matter. Okay, aka displacement, if you're more familiar with that word. What about total distance? A little bit more involved with this one. Yeah?
Like all the distance if you went back and forth.
Right. So for net distance, we don't care if we change direction. We're just looking at beginning and ending and the difference between the two. If we do change direction, though, that is important for total distance, because if we change direction, we have to add up those individual distances, how much we travel to the right versus how much we travel to the left. So there's a little bit more calculation to do for total distance. What if we don't change direction? How are net and total related? They're the same. Okay, perfect. So let's check this one out. The position of a particle is given by this function, measured in feet, so we have some units. Find the net and total distance, interval pi over 6 to 5 pi over 4. All right, so for net distance, it's strictly beginning point, ending point, and the difference between the two. So maybe we'll do position at pi over 6. We'll subtract the position where we end at 5 pi over 4. Okay, you might need your calculator. So take a few moments and plug in pi over 6 and 5 pi over 4. Make sure you're in radian mode too, because we're dealing with trig. All right, so if I plug in pi over 6, I got 1.5236, and 5 pi over 4 gives me 2.51278. Okay, more decimals you have, more accurate you are. Technically, we shouldn't round until our final answer, so maybe, I don't know, I'll make this 5.9 instead. Okay, so if we're going to subtract the 2, we're clearly going to get a negative number. But distance cannot be negative. Okay, direction can, distance cannot. So that's why we sometimes put these in absolute value bars. That way we just ignore the negative if we happen to get one. So 0.989, you can chop it 1 or round to 2. Trunk or round, doesn't matter. Units would be feet. All right, so if we strictly look at beginning point, ending point, this was our displacement. For total distance, however, we kind of need to figure out if we change direction anywhere within this interval. So how might we want to find that a changing point if one exists? Yeah?
Sign chart to find max or min.
Sign chart for max or min, and in order to do a sign chart, you got to figure out those derivatives, critical points, okay, all that jazz. So let's go ahead and find the derivative of position. We can label that as velocity, or you can do p prime, doesn't matter, they mean the same thing. So if we take our derivative, you can write x's instead of t's if the t's kind of throw you off. We'll have 1 plus 2 cosine. All right, set it equal to 0, and we'll try to find these critical points. So subtract the 1, divide the 2, and unit circle time. Might be a little tricky. Can we think about where on the unit circle cosine has a value of -1/2? If cosine's negative, if the x value's negative, we know we're in 2 or 3. Okay, so can we find some times, some radian values within quadrants 2 and 3? If you have a unit circle, it's on page 10. Two pi over 3 and 4 pi over 3. All right, so looking at these two critical points and noticing how the interval is pi over 6 to 5 pi over 4, 2 pi over 3 definitely falls within the interval, but I think 4 pi over 3 is a little bigger than 5 pi over 4. Okay, because 4 over 3 is 1.33333 and 5 over 4 is 1.25. So this one we actually don't have to worry about. So let's test this one. We'll do pi over 6 to 2 pi over 3, and then 2 pi over 3 to 5 pi over 4. All right, can we think of an easy and radian value between pi over 6 and 2 pi over 3? Let's see, if we think about pi over 6, that's somewhere in the first quadrant, and then 2 pi over 3 is somewhere in the second. Is there an easy radian value between those we can pick? Pi over 2 at the top, okay? So cosine of pi over 2 is 0 times 2, 0 plus 1, 1. So that's positive. So next we got to pick something between 2 pi over 3, so that's in quadrant 2, and 5 pi over 4, which is in quadrant 3. Pi, okay? Cosine of pi? -1 times 2 plus 1? -1, so that's negative. Okay? So we do have a sign change, yep, so we change direction. All right, so we have to calculate individual distances. Notice how based off of our sign chart, we know where we're moving to the right, okay, the interval where that happens, and we know where we're moving to the left. Okay, I'm assuming we're moving left and right. They didn't really specify. It could be up and down that direction, but at least we know positive and negative directions. So let's see if we can find some distances. So I'm just going to keep adding to this chart. So let's go ahead and calculate the distance between these 2 points. Basically displacement on this interval. So if we plug in pi over 6, we actually already know what that number is because we did that previously for net. So now we just got to plug in pi over 3 and subtract the 2 and see what we get. So let's see, I'll go ahead and type in 2 pi over 3. All right, and I got 3.826. So if I find the difference between this number and the 1.52359 that we had previously, we'll get 2.30286. Okay, this is not my final answer, so the more decimals I have, the better I'm going to be. All right, So for the next interval, we're going to do the distance between these points. So I need the difference of 3.28644,591 and then the 2.51278 that we had before when we plugged in 5 pi over 4. So I get 1.31366. All right, so we know how much we move to the right, and now we know how much we move to the left. So total distance would just be the sum of those two numbers together. So 3.6165. Okay, this one we'd have to keep it at 5 because the 2 would not round it up. And our units were feet. Good review from yesterday? Coming back? Okay. What we're going to spend the rest of today on, though, is looking at kind of free response type questions. I don't know if these have actually shown up on previous AP exams. It didn't really specify where I found them. But these are good free response examples nonetheless. So the first one is non-calculator. Let's not be tempted to use that one. All right, a particle moves along an x-axis, so we know we're only moving left or right, and its position at any time is greater than 0, and they give us the position function. We're measured in feet and also seconds, so we do have some units. All right, part A, find the average velocity on the interval from 1 to 2. Make sure you use units. How can we find average velocity?
2 points.
2 points. 2 points on what? 2 points on velocity, 2 points on acceleration, 2 points on position. We got to be... Let's think. Velocity is the slope, aka derivative, of position. So we basically, if we want an average slope of position, we're going to need 2 points on position itself. So we're going to plug in 1 into position, plug in 2 into position, and then we'll calculate the slope between those 2 points. Okay, no calculator. So, hello. Who are we looking for? Griffin, go ahead. Thanks, Brianna. Okay, so if we plug in 1 minus 4, negative 3, minus 3 more, negative 6, plus 1, negative 5. All right, next we got to plug in 2. 2 cubed is 8. All right, so we'll do 8. 2 squared, 4, times 4, 16, and we're subtracting that. Minus 6 plus 1. 8 minus 16, negative 8, minus 6, negative 14, plus 1, negative 13. Okay, so we have our 2 points. We're going to find our slope. So we need the change in the y's. You're subtracting in negatives. Make sure you change it to a plus. Over the change in the respective x's. Looks like we'll get negative 8 over 1, which would be negative 8. Now they do want units. So this negative 8 is an average velocity. So we're going to need a velocity unit. Feet per second. Good. All right, let's try B. On which intervals of time is the particle moving to the left? How can we figure out direction of movement? Velocity, sign of velocity. Okay, velocity tells us direction and speed. So we got to figure out velocity and when it's negative in this case, because we want to be moving to the left. So how can we figure out our velocity function? Take the derivative of position. All right, so 3t squared minus 8t minus 3. We want to figure out where this is 0. Since it's a quadratic, I'm praying that it can factor, because if not, we're going to have to do the quadratic formula. So, can it factor? Can we think of two numbers that multiply to negative 9 but add to negative 8? Yeah. Negative 9, positive 1. I do divide and slide technique, so I'm going to take that 3 and divide it. So t minus 3, and then this one would become 3t plus 1. You've never seen divide and slide?
Yeah, you taught me that over the summer.
Over the summer,
Yeah.
okay. Are we okay with this? A times C add to B? Have we seen that before? Yeah? Okay, so when I think of two numbers that multiply to negative 9, add to negative 8, I get negative 9 plus 1. So I'm going to write those in my factors. Now, normally we just stop there if this A value is 1, but that's not the case here. Okay, the A value is 3. So a little math magic. You can take this 3 and divide it by those special numbers that we found from over here. And 9 divided by 3 simplifies to 3. Since this one does not simplify, you slide the 3 as a coefficient in front of the variable. It's called divide and slide. So, divide by A, slide if it doesn't simplify.
Yeah, because Mr. Contact never taught us.
I don't
And
know.
I learned it over
I know my pre-calc did it last year.
Yeah, I learned it over the summer for the summer word thing.
If you didn't factor this way, you'd have to do grouping, which would be four terms, okay? But that would work too, okay, either way. So if factors, which is nice, can we find our times? 3 and negative 1/3. Okay. So let's go ahead and figure out when we're moving to the left. Now, when we did polynomials, we always did negative infinity to positive infinity. But for these particle motions, they might be a little bit more specific with their time. Notice how they told us t was greater than 0. So we, I guess, can ignore the negative 1/3. Okay, we're not going to go in the past. So we'll go from 0 to 3, and then 3 to infinity. And we'll test our derivative function, aka velocity. So anything between 0 and 3. 1. Okay, plug it into your factors. The first factor would be negative if we plugged it in. Second factor would be positive if we plugged in 1. Negative times positive, negative. Anything bigger than 3. 4. Okay, plug it in. First factor, positive. Second factor, positive, multiplied together, positive. Okay, so on which intervals is the particle moving to the left? We can say 0 to 3 because velocity is negative. We also might want to take note that if velocity changes negative to positive, then that means we're changing our movement from to the left to the right. So we do have a change in direction at 3. Okay, make note of that because, I don't know, it might come up in the future. But at least we have that analysis now. Okay, let's go ahead and try C. Using appropriate units, find the value of P prime of 3 and P double prime of 3. Based on these values, describe the motion of the particle. So if it's asking for the derivative of position, what does that represent? Velocity. So P prime is actually representing the velocity at 3. And what about the second derivative of position? That's acceleration. Okay, so we might have to figure that out. Let's do maybe velocity at 3 first. If you plug in 3 to our velocity function that we did in part B, we're going to get 0, right? That was where we changed direction. Velocity was 0. Acceleration, though, we're going to have to do another derivative. So that'd be 6t minus 8. And what if we plug in 3 there? 18 minus 8, we get 10. Okay. Using appropriate units. Can we tack on some units to the 0 and the 10? Feet per second for velocity. And what about acceleration? Feet per second squared. Okay, so based off these numbers, it says describe the motion of the particle, give a reason. So if the velocity is 0, but the acceleration is not 0 in this case, what's the particle doing? If you're not moving, but you somehow are accelerating, you're rotating. Okay, aka if we're only moving left and right, you rotate to change direction. Okay, so we'll say the particle is changing direction at time 3 because velocity is 0, but acceleration is not. That was actually one of our, I think there were 5 commandments, those 5, bless you, those 5 important characteristics of particle motion. This was the last one. Okay, if you're not moving but you're accelerating, that means you are rotating. Okay, your position isn't changing, but your speed is because you are rotating in some path. Yeah.
So is it rotating like 3-dimensionally?
What do you mean by the 3rd dimension?
I'm just kind of confused. Where is it rotating to?
So this is telling us from 0 to 3, it's moving to the left. If its velocity is 0, that means it's stationary at this time. And then on this interval, it's moving to the right. So what we're looking at is at time 3 here, if you're stationary, your velocity is 0. But the fact that we're accelerating means that you have that rotation. You have some type of movement.
But it's still moving on the same axis.
It's still moving on the same axis. It's only moving left and right. Okay, but if you're not moving but you are accelerating, that's what's causing the turn. Okay, that rotation. All right. D, what is the maximum velocity on the interval? How can we figure out the highest velocity? Find the max, aka slope of 0, right? So slope of velocity would be acceleration. Can we figure out when acceleration is 0? At what time? Let's see, if we set equal to 0, add the 8, divide the 6, 4/3, okay? So if we're trying to find a maximum, this is a potential spot, right? Because it's a critical point. But where can an absolute max also happen? Yeah?
In this case, 1 and 3.
1 or 3. It can happen at the endpoints. This is kind of our extreme value theorem. You're guaranteed to have a maximum at an endpoint or a critical point. So these are the endpoints. Here's our critical point. We're going to go ahead and test those in our velocity function. So I didn't mean to put t there. We'll do v of 1, v of 3, and v of 4/3. All right, now it might be easier for us to plug these numbers into the factors of velocity instead of the quadratic, but either one would work. If I plug in 1, my first factor would be -2, my second factor would be 4, multiplied together, -8. If I plug in 3, my first factor is going to be 0, which multiplied by anything else is still going to be 0. If I plug in 4/3, yeah, I know. 4/3 minus 3. 4 minus 9 would be -5. So -5/3. And then if I plug in 4/3 into the other factor, the 3's would cancel. I'd be left with 4 plus 1, which would be 5. So negative 25 thirds. Okay, so they're looking for maximum velocity. Out of all of these options, which one is the highest, the max?
No.
This is careful. If it says maximum velocity, right, that's with speed and direction, so we got to take both into consideration. Out of all of these, which one's the highest?
Are you kidding me?
It'd be this one, right?
That's ignorant.
Okay, this is absolute max or absolute velocity. What if it said maximum speed? Then it would be this one, right? Because 25 over 3 is the biggest number, you ignore the direction. Okay, there's a difference between the two. So this would be your max speed. Okay, the 25 over 3. So we have to be careful in the wording. Velocity, we're just looking at the number itself, or with the negative, okay, the biggest number overall. The speed, on the other hand, we don't care about the negative. So we're just going to look at the number itself. Okay, a little difference between the two. So this one they wanted maximum velocity. So that would be 0. All right, last one, part E, kind of run out of room. Find the total distance the particle moves from 1 to 5. Do we change direction anywhere from 1 to 5? Yes, where? 3. Okay, so we need distance from 1 to 3, and we need distance from 3 to 5, that ending interval, and then we'll add them together. So let's see, if we plug in 1, we already know we get negative 5. So we just got to figure out what happens if we plug in 3. All right, can we plug in 3 into our position function? 3 cubed, 27. 3 squared, 9 times 4, 36. Minus 3 times 3, 9, plus 1. Okay, 27 minus 36. Minus 9 more. Plus 1. Negative 17. Okay, so negative 5, and then we have to subtract negative 17. So that would change to a plus 17. So it looks like we moved 12 units on that interval. For the next one, we'll take negative 17, which is the number we just found, and we're going to subtract our position at 5. We're going to have to go ahead and figure that one out. All right, let's plug in 5. 5 cubed. 125 minus. Okay, 5 squared. 25 times 4, 100. Minus 15 plus 1. So 125 minus 125 minus 15. 10 plus 1, 11. Okay. Negative 17 minus 11. Negative 28, right? But we don't care about the negative because this is a distance. We're essentially taking the absolute values of these. So total distance, 12 plus 28, 40 units, feet. Here we go. All right, that was quite involved, but we did a lot. Okay, we answered quite a bit of information about this particle. Let's go ahead and try the last one. We might not be able to finish it, but we'll see how far we can get. All right, this time we have a table example. So we'll see how this one operates. A test plane flies in a straight line. Maybe we'll assume left and right. Velocity is given in a table, units, miles per minute. We know velocity is differentiable. What else do we know about it? It's also continuous. All right, continuous too. Selected values are given. Okay. Find the average acceleration on the interval from 5 to 20. Acceleration is the slope of velocity. So we need 2 points on velocity, specifically from 5 to 20. So,
pick 5 and 20.
yep. So 5 and 20.
That was a good one.
We need change in the y's, okay, subtract the y's, over the change in the respective x's. So it doesn't matter how you set it up as long as you're consistent on how you do so. We can use a calculator for this one, might not be too bad.
Yeah.
9.2 minus 5.4, 4.7, over negative 15,
Just over.
0.3133. Express your answer using correct units. This is an average acceleration value. So we need acceleration units.
Miles per minute squared.
Miles per minute squared. Good to go. All right, based on the values in the table, on which intervals is the acceleration of the plane guaranteed to be 0? So are there some points in time here, some intervals, where the acceleration is 0? Where the slope of velocity is 0?
25 to 30.
Yes.
25 to 30, what's special about those?
Flat.
Same y values.
Line, baby.
Flat line somewhere, right? Rolle's theorem, endpoints are the same, slope is 0. So we'll do 25 to 30. Are there any other ones?
5 and 10.
5, ooh, not quite. They're not the same. They're close. What about 0 and 15? 7 and 7?
If it's between 5 and 10, so.
All right, so it says, justify your answer. Because, okay, if this is essentially Rolle's theorem not explicitly stated, we need to show how the conditions of Rolle's theorem are met. What are the conditions of Rolle's?
Equal endpoints.
Because V of t has equal endpoints, okay, on those intervals. And what's a condition for like every theorem we've had this year?
Continuous.
It's continuous.
Good job.
And V of t is continuous. And differentiable. Okay, Rolle's had those 3 conditions. Continuous, differentiable, and endpoints are the same. Looks good. Maybe you want to put Rolle's in parentheses just as a reminder if you go back to this question. All right, C. Does the data represent velocity values of a plane moving away from where it started or returning to where it started? Give a reason for your answer. So it's kind of asking us about its direction of movement. Is it moving away from where it started or back to where it started? How do you know?
All the velocities are positive.
All the velocity is positive. So that means your position is increasing. If velocity is positive, that's the slope of position. So velocity positive means you're moving in a positive direction. If it's negative, you'd be moving back. Okay, kind of you changed direction and went back to where you started. So we'll say away from origin because V of t values are positive. Now, I know that you might think, well, Mrs. Bauer, isn't there a gray area? Like, we don't really know what's happening in these points, like in between them. But you got to take a look at the wording on the question. It says, does the data represent velocity values? So you're just taking a look at the numbers that they give you. Okay, does this data tell you something? Okay, something might be happening in between, but based off of what we have, we can make this kind of assumption, if you will. All right, D. The function defined by that stuff is used is used to model the values in the table. Yeah,
I was gonna ask a question about C.
yeah.
Wouldn't, if all the values of, like, V of T have the same sign, wouldn't it be, like, moving away regardless, like, even if it was negative? Because it could be going away from the origin, just in the negative direction.
So that's when we'd have to kind of figure out how much we move to the right versus how much we move to the left. And we're not quite at that point yet. We're going to focus on that criteria in Unit 6 a little bit more. So what's happening? So if we did have some negative values, that would mean we're moving to the left. But we would have to take into consideration how much we move to the left. So there might be a point in time where we are going back, but we don't know how much we're going back.
I mean, I was just saying though, like,
If every single number was.
if every number was negative, wouldn't we still be moving away? Because,
Yeah, like if you started over here and we're going.
Yes. Well, okay. So if every single number was negative,
You're still going away.
then you'd be moving away. That's true.
Yeah, so-
Okay.
So
That's facts.
so she's saying that the justification is because they're all positive. Like
yeah,
they're all-
that's,
Yeah.
that's what I'm saying, yeah.
Yeah. Because V of T values are, maybe I'll throw in the word always in here.
Yeah.
Always positive. Not just the fact that they
Yeah.
are, but
Yeah, yeah,
it's always that way. All right, let's see if we can get this last one in. Function f, used to model the velocity of the plane. According to this model, what is the acceleration of the plane at time 23? Okay, how is acceleration related to velocity? Derivative. Okay, so we essentially have to figure out the derivative of this function, plug in 23. Do you want to do that by hand? No, because we are able to use a calculator, correct? It says calculator active. So let's go ahead and use that. Math, option 8. First box, always x. Middle box is the function. So 6 plus cosine x divided by 10. Close it off. Plus 3 sine of 7x divided by 40. Close it off. We want to plug in 23. All right, chop at 6 or round to 7. Okay, so we'll say acceleration at time 23 is negative 0.407. Chop at 6, round to 7, doesn't matter. Can we put units? Miles per minute squared. Okay, so there's our value. What does this value indicate about the velocity at this time? Decreasing, right? Acceleration is the slope of velocity. And if your slope is negative, then your velocity is going down, aka decreasing. So we'll say V of t is decreasing because acceleration is negative. So I guess you could say V of t is decreasing at this rate, because acceleration is negative. Okay. We're good. Coming together? Clicking? Okay, we're going to have a practice day tomorrow. All this particle motion business.